All right. Let's see. So today, I was double checking last night. It looks like we decided today was the due date for the midterm, and at midnight, that is. All right. So, keep going. Just keep working if you haven't already sent it in. Anyway, and if there's still any last minute questions, you can certainly feel free to ask them by email or whatever. And so, in the meantime, we need to go back and revisit where we left off. And let's see, I think we're getting towards the end of chapter 4. Yeah, this is the only class I have that meets once a week. So it's like every week I have to almost start all over again. What are we doing here? Yeah, twice a week makes a big difference, doesn't it? So let's see, here's Moodle. I think I've had that. Yes, we have to prove our identity to get our emails. Yep. Hold on. Here we go. Okay. All right, so here we go. Pre-calc. And we were somewhere in 4. Let's go find it.
Excuse me, I got a
Yes.
quick question.
Go ahead.
I don't know if we can do this now, but just in case, I was wondering, for the midterm solutions,
Mhm.
we
You mean
did last
sample
week.
sample
Yes.
midterm.
The sample midterm
Yeah,
solution.
they're right here.
Can we look at question 22 real quick? Is that
All right.
possible?
Sure, why not?
Because I was looking over that on the midterm as in a reference, and I think you forgot to foil it, and I just want to make sure.
Okay. All right.
I
Let me
think
just
so.
let me just double check. I don't even remember. Number 22, you say?
Yes.
Okay. Wow. Look at all these questions. Yeah, that was a big one, wasn't it? Look at all of those answers. Ooh, that was a marathon session. Okay, so what part are we looking at?
I think you forgot to foil the hold on. When you put it when you put G of G and never mind. There's no exponent. My bad.
Yeah, no, in a case like this, there's no need for FOIL because you're just multiplying the whole thing.
Yeah, you're just distributing. I thought
Exactly.
I thought I saw an exponent. That's why.
Oh, no, that's okay. No, you should ask questions if you're not sure. So yeah, this is everything we did last week. Woohoo, that was a long session, wasn't it? So all right, that's good. So that's all over with. So you can carry on. And you still have the rest of the day to finish it up. And if you're not sure what's going on about something, you can still send me emails. I'll try to catch up with them as fast as possible. And now in retrospect, I'm looking at this like, wow, that's a lot of reviewing. But you know what? We covered everything, and I think you find that your midterm, maybe I'm hoping you'll find that it's not quite as hard as you were expecting. I try to focus on the most straightforward concepts. So, all right. Anyway, so let's get back to it. So it looks like with chapter 4, we haven't actually looked at it in a while. There aren't any notes here. Here we are. This last time was 2 weeks ago. So I guess we must have spent the whole period last time just with this reviewing. And that's understandable. That was a very long sample midterm, but it really covered everything, didn't it? If you understood what we were doing, you're in excellent shape. Now, what's coming up next, of course, chapter 4 is exponential logarithmic functions. And, we've been making a lot of progress with this. Let's see, where did we leave off? I think we were getting ready to look at applications. Yes, I can tell because there isn't a whole lot of handwriting. All right, even if we didn't, if we did some of this already, we may as well start here again, because this is one of the more interesting applications of exponential growth. And if we do manage to finish this today, we're going to dive into 5. Now, 5 is really a major break with what we've been doing, because it's something you've seen before, maybe not for a long time. All of a sudden, we're delving into the world of trigonometry. Oh, remember sines and cosines and tangents and cotangents and all this good stuff? That's chapter 5. So we're going to spend not a ton of time, but some time reviewing our trig functions. So the reason for that is because they'll show up in a lot of applications, and you don't want to forget completely how these concepts work. So for 5, we'll just be looking at trig functions, and then we're going to move into something again, which is quite different than the rest of the course. We're going to dive into an area which is more part of what we would call discrete math, but we'll get to that down the road. So today we'll see how far we can get in 4, and maybe we'll take a quick peek at the trig functions, which, if you've forgotten everything you ever learned about trigonometry, it doesn't matter. We're going to start from scratch and start all over again and review what all of these concepts mean. And we most likely will be taking it to sort of a more complex level where you can get more deep insights into how this actually works and what it's all about, how these concepts are related to each other, as opposed to simply just memorizing sine of 90, cosine of 90. We want to understand what's causing these values to be what they are. Okay, so there's the focus in this chapter will be on understanding. We don't want to memorize, because in high school, they may have had you memorize some of the basics like cosine 90 and cosine 60, tangent 60. We're not going to memorize anything here. We're going to understand where all these results are coming from. Now, for certain disciplines, trig functions are very important, like engineering in particular, architecture, anything where there's physical building taking place. These are going to come in very handy. Other areas of study, like most business applications, you'll never see these ever. So you never know. It's hard to say with math when you're going to need it and when you're not going to need it. But having said that, chapter 4, this discussion about interest is something that you'll bump into in your daily lives, at least once you've graduated and you find yourself with money to save, or possibly looking to borrow money, let's say to buy a car or a house. This topic is extremely applied because you'll run into this all the time. In fact, it's going to be hard to escape interest rates because they affect the cost of just about everything that you do. So what's going on here? Now, obviously, as you know, this is when you lend money, you expect to get the money back, and you also expect to get interest. The question is how much interest is being charged for a loan. Also, if you lend money, let's say you put your money in the bank, you're lending money to the bank, and they will pay you interest as well. And again, the question becomes, how much interest are they paying you, and how do you figure out the exact amount? So whenever you earn interest or pay interest, there's only 2 basic types of interest that are relevant here. First of all, interest that's paid on the original principal, or the amount that's been borrowed, is down here. You can see it's called simple interest. And interest that's earned on previously paid interest is called compound interest. All right, so remember, interest on principal, where principal is the amount borrowed or lent, is known as simple interest. Interest on interest is called compound interest. And it's the compounding interest that's going to ask us to use some of these concepts we've seen in chapter 4. The simple interest couldn't be more straightforward. It's basically a linear relationship. It's the compound interest where we start to run into exponential functions, okay? Because the relationship between the interest and the principal can be seen as an exponential relationship. So we'll start with a very simple example, just to get the ball rolling. An investor deposits $1,000 in a bank that pays a 5% rate of interest. So we'll start with a simple case where the money is, or the interest is credited to his account at the end of the year. Okay, so when the year is over, the bank credits your account with 5%. The question is, oh, hold on one second. I have to answer the door. All right, I'll be in here. Now, you want to use the box. Oh, this one. Here is this going to come down. Oh, this is not. Oh, crap, this is. I can help you move. Just so that. All right, that should be good. All right, okay. All right, I'm actually doing an online class in here, but I'll be right here for you. All right, no worries. All right, sorry about that. I'm getting repairs done in my apartment. All right, anyway, so let's see how much money the investor earns by keeping the money in the account at the end of the first year and then at the end of the second year. So now 5% of 1,000 is $50. So very easy. This is a very easy idea. At the end of the first year, the account balance will be $1,050. Okay, so you look in your bank account and you say to yourself, wow, I've got $1,050 in my account. Where did all that come from? Well, obviously the first $1,000 is the principal that you invested in the bank. The rest is the interest that the bank credited to your account at the end of the year. Now, this is where it gets interesting though. At the end of the second year, if you don't touch your money, you start with $1,050, which then at the end of the year, you get another 5%. This time the balance goes up to $1,102.50. Now, you might have thought, if you didn't know how this works, that at the end of the second year, you would earn another $50. So look what happened here. So the difference between the 2 years is more than $50. All right. Hold on one second. 1,102.50 minus 1,050 is $52.50. So in year one, you earn $50 worth of interest. Year two, you earned $52.50. Now, here's the big question. Why? Why did you earn $250 extra in year two? Well, in the first year, this $50 was based exclusively on the principal that you started out with. At the end of the second year, your 5% interest is being based on both the original principal and the $50 interest you earned during the first year. So the $50 in each of those 2 years is known as simple interest because it's based exclusively on that principal. The rest of it, the $250 that you have here, is what we mean by compound interest. Okay, so for the first time, we're seeing both simple and compound interest. So at the end of year two, we're getting both simple and compound interest. In year one, this is 100% simple interest. Now, if you leave the money there for another year, what will start to happen is you'll get even more interest. Okay, so so here, for example, you can see it broken down more. Of the $1,102.50 at the end of year two, You still have your original 1,000 in principal. And the remaining 102.50 is clearly interest, but now we want to know how much is simple and how much is compound. So 100 is the simple interest. Now, how do you know that? Because like we said, with a $1,000 principal, a rate of 5%, and a time frame of 2 years, if you multiply those three together, PRT, you'll end up with $100 worth of simple interest. Okay, the rest, the remaining 250, is therefore compound interest. Oh, excuse me. Oh my God. All right, sorry about that. I was getting some very important repairs done to my apartment. And, I didn't know they were coming at this hour, but I'm happy that they were here. So anyway, so the idea here is we can figure out not only how much interest we've earned, but how much of it is simple and how much of it is compound. So, and by the way, you know what I'd like to do here? Let me just quickly show you how that can pile up over time. I'm going to open up Excel. And what I'd like to do is just quickly show you how quickly the interest can grow over time using the same setup. We'll have once a year. We'll start out with $1,000. So year zero means you're just starting out. And you have interest. The first year you have no interest. The rate is 5%. So the interest, actually, let me call this year one. That might make it easier. So you'll get 1,000 times 1 plus 0.05. Now, the simple interest will never change. Actually, let me call this balance. Oh, wait, I did something wrong. The interest is not 1,050. It's 50. All right, don't worry. This will only take a minute. If you've never used Excel before, this is a golden opportunity to see what it looks like. Okay, so again, the rate is 50, 5%. The principal is 1,000. The simple is 50 every year. Year one, let's do this. Initial balance is 1,000. The interest is 5% of the $1,000. We'll call this total interest. The simple interest is 50. All right. And then, let's see, hold on. The compound interest is the difference between the two. Now, in this first year, there is no difference. And then what we can do is put the ending balance. And that's going to be the initial balance plus the total interest. Okay, great. So far, this is exactly what we've seen. In the beginning of year 2, we have 1,050. The total interest is 5,250, of which simple is 50. The difference is 5,250. So this is basically where we left off. All right. So now I'm going to show you the rest of it. What I'm going to do is extend this out for several years. Let's say, I don't know. How about, let's go out 10 years. Just out of curiosity. Oh, no, something went wrong. All right, so let me see if I can drag this out for 10 years. So what I want you to pay attention to is the pattern of the compound interest. All right, it seems to be working now. So in other words, what's going on here is that every year that goes by, the balance is of course growing, the total interest is growing, but if you see, the simple interest is always $50. It's that compound interest that's growing very, very quickly. Here it was only 250. Here it's 27.59. And so if I kept pushing that out, let's say to 20 years, what you'll discover pretty quickly is that after a while, the compound interest will be more than the simple interest, which you can see. In fact, it started right about here in year 15, they're more or less the same. So if you were to draw a graph of how this works, let's get rid of this. A graph would look something like this. Okay, so what you can find is that you've got dollars, you've got time. So your simple interest will grow. It's a straight line. It's a linear function. In this case, $50 a year. The compound interest starts out very slowly, but after a while, it starts to catch up. And so it doesn't, well, it's hard to draw properly, but what I'm trying to get at here is that it starts to very much resemble an exponential function. All right. So you'll see under what conditions it actually is exponential, but that's the part that's growing like crazy. And so this is the part that in the long run accounts for most of your return. So what this means then is that if you, let's say you're saving for your retirement, the sooner you start, the better off you are, because the compound interest grows very, very quickly as you get further out into time. And so you can use these concepts to do your own financial planning in the sense that, look what happened here. If you were to, let's say, retire in 20 years, all right, well, obviously not, but let's say 20 years from now, you're planning on retiring, your initial $1,000 is now worth $26.5330. So if you start out with $100,000, you've got $265,000, et cetera, et cetera. So you can figure out by doing these calculations how much your savings will be worth in the future. And that's a very valuable tool to have when you're planning for the long run. Like I said, this won't really be relevant to you until you're out there working it, but this is important information. Now, this is where it gets interesting, though. What if we change our assumptions? What if instead of the bank paying you interest only at the end of the year, right? In other words, not waiting to the end of the year and giving you 5%. What if instead twice a year they gave you half of that, or in other words, 2.5% twice a year? Would that make any difference in the results? Or what about if they gave you, instead of 5% once a year, 1.25% 4 times a year? Would that make any difference in the amount of interest that you earned? Well, the answer is yes, but this compounding frequency, I'll just sneak it in here now. The frequency with which interest is paid each year is known as the compounding frequency. Okay, and this will affect the compound interest, but not the simple interest. And furthermore, we'll discover in a few minutes that as the compounding frequency increases, the compound interest earned will also increase. So you're actually hoping that the bank doesn't pay you just once a year. Even if they break it up into 4 equal pieces, you're going to get more simple interest than you would, compound interest than you would if they simply did it once a year. Now, the terminology we'll use is this. When interest is paid once a year, we call it annual compounding. Twice a year, we'll call it semi-annual compounding. 4 times a year will be known as quarterly compounding. And you can figure out the rest too. For example, 12 times a year would be monthly compounding. And then, of course, 365 days a year would be daily compounding. All right, so what we're going to do is tie all this together with a nice formula. What this formula is going to tell us is that if we start with P dollars today and invest it for T years at a rate of interest of R, N is the compounding frequency, A is the amount we'll end up with. Now, I know that's all very abstract. So on the next slide, I've repeated the formula with all the identifying variables. So P, you recognize P is the principal that we started out with. R is the rate of interest. And by the way, when you see a rate of interest quoted, it's understood that it means per year. Okay, that's an annual rate. T is the time. Again, it's always assumed to be in years. N is how many times a year is your interest compounded. So in other words, for example, quarterly compounding means N equals 4, just as an example. And then A is something we call future value of the sum. If you look at the chart that I just created, these are also, it says ending balance, but you can think of that as the future value of your deposit. Okay, so in other words, how much will you have in the future? This is the A in that formula. Okay, so we're going to use this formula to calculate multiple things. We're going to calculate not only the future value, but how much interest we earned, of which how much is total, how much is simple, and how much is compound. So it's a very useful formula. Okay, now, why don't we start? Well, first of all, remind ourselves that the compounding frequency, as we've said, N, refers to the number of times a year that the interest is paid to our account. So there's only realistically a few possibilities here. Twice a year, 4 times a year, 12 times a year, and 365 times a year. All right, so why don't we start out with some important formulas here. All right, sorry, I was just checking something. We're going to calculate first simple interest, which we've already done. That PRT that you see down here is what we're going to do to calculate simple interest. Okay, and remember, P is principal, R is the rate, T is time. So we're going to do this in a very simple way. We will be able to figure out the total interest by doing the following. That would be the ending balance or future value minus the original principal. Whatever's left over is the total interest. Okay, now of the total interest, we know that some of it is simple. The rest is compound. Now we have a formula for this one. We don't have a formula for compound interest. So instead, what we're going to do, we're going to take total interest and subtract from that simple interest. And that's how we can decompose our results into total interest, simple, and compound. Okay. All right, you'll see. It sounds a lot more complicated than it is, really. All right, here we go. So we start out by borrowing $10,000 for 3 years with the annual rate of interest is 6% compounded monthly. That's what we're looking for. How much interest will we pay during the lifetime of the loan? All right, so based on what you're seeing here, the principal borrowed is $10,000. Time is 3 years. The rate is 6. And the compounding frequency is monthly. So we have everything we need to know to calculate the future value of the sum, meaning what will be our balance at the end of 3 years. But if you notice, we're actually getting paid monthly. So at the end of 3 years, we will have received 36 interest payments. Here's something I want to point out though. Each time you get paid, you're not going to receive 6% though. That's the annual amount. Instead, you're getting 1/12 of that, which is 0.5%. So there's 0.5% 12 times a year rather than 6% once a year. Okay, now, so yes, we know this. Let's plug in the numbers. And you'll see that you've got 10,000 times 1 plus 0.06 over 12 raised to the 12 times 3 power. Now, if you're going to evaluate this on your calculator, probably what you should do is simplify it as much as you can. For example, this ratio is 0.005. This exponent is actually 36. So what I think you should do is calculate this piece first. Okay. 1.005 raised to the 36th power, whatever that is, you can then multiply it by 10,000, and this will be your ending balance or future value. Now, in this case, it's a loan. So it still amounts to the same thing. In other words, this is how much money you're paying back to the lender. Now, clearly, that's more than $10,000 where we started out. So what is causing it to be higher than $10,000? All right, well, let's break this up into its individual components. So we can start by figuring out how much total interest there is. And then we'll break that down into simple and compound interest. And you'll see how straightforward this really is. All right, so given that our future value is $11,966.81, we know that 10,000 of that was the original principal, which implies that we must have paid 1966.81 in interest. Okay. And that's where it gets interesting. We can break this down further into simple and compound interest. All right. So remember, the formula for simple interest is just P times R times T, or principal times rate times time. So if you multiply these out, you get 1,800. And if you subtract that from our total interest from the previous slides, 1966.81, that implies that this last piece, the difference, is our compound interest. All right, so in other words, we know that we paid 1966.81 in interest. 1,800 of that was simple interest and charged on the original principal. The rest is compound interest. And it's only 3-year loan, so you can see it's not a huge amount compared to the simple interest. But if this was a mortgage on a house, for example, that lasts for 30 years, the compound interest could be quite considerable. In fact, it'll probably be more than the simple interest. All right, so, and by the way, I just want to mention right here, if the compounding frequency was, let's say, every day, this would not have affected the simple interest, but it would have increased the compound interest. All right, so it's only the compound interest that's affected by the compounding frequency. All right, here we go. Now, here's what we're going to do with this one. We have an investor that deposits $1,000 into a 1-year account. So we'll keep it simple, 1 year, that pays an annual rate of 4%. And what we're going to do is try to figure out the future value or balance at the end of the year under these 4 different assumptions about compounding frequency. So the way this problem is written, A is what we're solving for. It's the future value or ending balance. In our example, P is 1,000, T is just 1, R is 4%, which, by the way, don't forget, when you're using interest rates in a formula, you should always convert it into a decimal. And then the N comes from these 4 parts. All right, so what I'm going to have you do is use this formula with these numbers and these compounding frequencies to come up with the 4 future values. And you're going to see that as we increase the compounding frequency, then the future value will grow because the compound interest is increasing. All right, so why don't you take out your calculator and a pen, I guess, and why don't you take a shot at these and let's see how you do. Sorry. Yes, you can tell I'm not in good shape today. Luckily, this is online anyway, but all right, so why don't you try those 4, and I'll give you a few minutes, and then we'll see how we did. All right, let's see how we did. So we know these are the values that we need. Now the compounding frequency this time is 1, n is 1. So this one simplifies very easily to 1.04 times 1,000, which is just 1,040. All right, so this is the first case that we saw earlier. There is no compound interest in this case. Okay, all of that is simple interest, all $40. So let's see why that happened. So the total interest is 40, obviously. The simple interest formula tells us that that is equal to 40 as well. So because they're equal to each other, that implies that there's no compound interest. This will happen anytime you have the money kept in an account for just 1 year and the compounding frequency is annual. All right. Any other case, there will be at least some compound interest. Okay. Now, in part B, that's not true any longer because you can see this formula in the parentheses is actually the equivalent of multiplying 1,000 times 1.02 squared. And when you multiply that out, you'll end up with $1,040.40. Now, the change is only 40 cents, but that's still, even though it's a small amount of money, that is still your money. So it matters to you a great deal. And so that 40 cents is our compound interest. The $40, this $40 is our simple. Hold on 1 second. Oh, wait a minute, what just happened? Yeah, this is our simple interest. The rest is the compound. So with only semi-annual compounding and only a 1-year investment, you can't expect the compound interest to be very much. But when we change the frequency, you'll see that it will go up. Okay. So in other words, altogether, our total interest is $40.40. And based on the simple interest formula, that's going to be $40 worth of simple interest, and whatever's left over is our compound interest. Now, let's jump this up to monthly compounding. And you can see it's getting a little bit more complicated here. The 4% divided by 12 is about 1/3% per month. So you can multiply 1.033333 to the 12th power and multiply that by 1,000. And you'll end up with approximately $1,040.74. This, of course, is our compound interest. This is our simple interest. And it went up from 40 to 74 cents. Okay, well, of course, that's what we would expect. It should keep going up. So if you're the borrower, if you're the lender, the person who's saving, this is making you happy. Sorry. If you're the borrower, this is not making you happy because it means you're paying more interest on your loan. So the compounding frequency will help, in this case, the higher compounding frequency will be helping the lenders, but hurting the borrowers. All right, and then the last one, the daily one, is a little tricky because 4% over 365 is a tiny, tiny number. Approximately 0.0001096, which when raised to the 365th power and multiplied by 1,000 gives us roughly $1,040 and 80.8%, cents rather. Now, in practice, the bank would round this up to 81 cents, but I just wanted to leave it like that for you to see it. And of course, just like all the other cases, $40 is our simple interest, and what's left over is our compound interest. Now, you might have noticed that when we went from, I built up a nice little chart here. What's interesting about this is that as you keep increasing the compounding frequency, the compound interest is growing, but there's a limit to how far it can go. And we're getting close to that limit when we get to daily compounding. And so notice, you notice how when we jump from annual to semi-annual, compound went up 40 cents. From semi-annual to monthly, it went up another 34 cents. from monthly to daily, it only went up by about 6.8 cents. Okay, why? What's going on here? Why is it slowing down? Well, this graph is meant to show you exactly what this is all about. As we increase the compounding frequency, the compound interest is growing at a progressively decreasing rate, and eventually it levels off and reaches a limit. And that limit means that the amount of interest, or the interest, is being compounded basically an infinite number of times per year. And that case, which of course doesn't exist in practice, is referred to as continuous compounding. Okay, so that's what we've been building up to all this time. This is where we suddenly find ourselves with an exponential function for the first time. So when interest is compounded continuously, or at every instant in time, we have an exponential function that determines how much interest we're going to earn. Okay, so what does the formula actually look like in this special case? We can't use this A formula any longer to calculate future values because n would have to be infinite. Okay, in other words, this formula can no longer be used because now n is infinite. So instead, we have to do something different. What is that something? Well, it turns out that if you keep increasing n, and you'll see this if you take calculus, by the way, it ends up converging to this formula, A equals P e to the RT power, where E itself is a constant, as we know, that's approximately equal to 2.71828. So this is actually an exponential growth function. Although it may not look like it, it is, because you can see the variable x, which in our case is the t, is in the exponent. All right, so now if I wanted to know, for example, what would happen if my interest was compounded continuously, based on this last case, okay, so if you look at this chart, at the bottom, we do not have the continuous case just yet. Let's see how close continuous compounding is to daily compounding. So let's see, oh, here we go. So again, we're putting $1,000 into the bank for 1 year. The interest rate is 4%, but now all of a sudden, interest is compounded continuously. So I need my new formula, my special continuously compounded formula. Okay. And so what ends up happening is if you take out your calculator, e raised to the 0.04 power is approximately 0.81. Sorry, hold on, let me get that out. No, it's 1.0408 10,774. Now that is multiplied by 1,000 to give us our final result, $1,040. Now here you notice it's 81.0774 cents. Okay, so it's not much more than the daily compounding case, is it? No. It's surprisingly close. Remember with daily, just a quick reminder, A equals 1040.808. So the difference is extremely small. In fact, the bank would round both of these to 1040.81. So you almost can't even tell the difference. Okay, but still, we can think of this as the limiting case. So I've completed our chart, so you can see how this happens. So now we've reached the limit of how much compound interest we can earn with this continuously compounded assumption. And again, if we revisit this graph that we did earlier, you can see this dotted line is the limiting case of continuous compounding. That's it. That's as far as it can go. Now, we're not going to have the opportunity, I don't think, to delve into this much further, but believe me, if you take a course in finance or something like that, or, you know, you never know what you might bump into in a more advanced course like Calculus 1, this will prove to be extremely important. Very important. And you'll see this all the time, especially in financial type courses or classes where you're talking about personal financial planning. This is important information to know, not just for its own sake, but because it could be very helpful to you when you invest your own money. All right. So anyway, so now we're going to look at the opposite case. All of this refer to what we mean by exponential growth. Okay. What about decay? Is it possible for a value to shrink over time? Yes, of course. For example, you might recall from high school that you studied physics and you learned about radioactive elements. They don't stay radioactive forever, do they? What happens to radioactive elements over time? They decay. The radioactivity eventually converts, the radioactive component of each element gradually converts into lead. And in fact, if I'm not mistaken, this is one of the ways that items can be, very old items, like the tombs in Egypt, can be dated by looking at these radioactive elements and seeing how much carbon they have in them, not carbon, how much lead they have in them after a certain length of time. So we have this notion of continuous decay to distinguish it from continuous growth. All right, so this formula could be thought of as continuous growth. This is because we have that negative exponent, it becomes continuous decay. Okay, now, what if we had a radioactive element? It could be any one of them. Let's say it's uranium. It decays at the rate of 5% per day. All right, every day 5% becomes lead. Eventually the element will be completely inert. It'll be all lead. If we start with 100 grams of this element, how much will still be radioactive after 10 days? All right, so the time is 10 days. It's 5% per day. So here, I just want to point out that in our other example, T and R were based in years. Okay, that's normal with financial markets. In this example, R and T are defined in terms of days. So as long as we're consistent, we can actually have any time frame we want. It's just that with finance, we tend to use only annual rates of interest and years for our times. Here, they're both days. So therefore, I don't have to do any converting here. This is 5% per day. And this is 10 days. So it's a rapid process. And you can see that after just 10 days, 100 grams of this radioactive element only contains 6.653 grams of radioactive material after 10 days. So if you could draw a picture of this, in fact, I'll tell you what, why don't we do this? Let's go to our old friend Simbo Lab and take a look at some of these, a graph. We'll start with A equals 1,000, E raised to the 0.05 power, okay? Let's see what that looks like. Oh, that's right, I remember we couldn't seem to make it work. I don't remember, what is the problem? Oh, I know what's wrong with it. I think I've finally figured it out. Let's call that X and see how it reacts to that. Okay, so in other words, now, of course, here, we have to be careful because with interest rates, we can't actually have a negative value. So the only relevant portion of this curve is right here. Oh my God. Well, okay. Okay. Well, I don't know if I can fix that or not, but let's see what the negative version looks like. It falls off very quickly. All right, that's the best we're going to get. Okay, sorry. I thought we could do better, but it's fine. Anyway, so then we're ready for logs. Now, logs are closely related to what we've just been doing. Logs are designed to make things simpler for us, as hard as it is to believe. Certain types of cases are easier to measure in terms of logs than in the original data. So let me give you an example of this. You've heard about the Richter scale, which is used to measure earthquakes, the strength of an earthquake. The Richter scale is a logarithmic scale, which means that if you hear in the news that a certain city had an earthquake with Richter scale 5, what they really mean is 10 to the 5th power. And so what that means then is that the difference between, let's say we have two cities that have an earthquake. LA has Richter scale 5, and Tokyo has Richter scale 6. It may not sound like a big difference, but that actually means 10 to the 5th versus 10 to the 6th. So the Tokyo earthquake is actually 10 times worse than the LA earthquake. So for certain types of units, it's like this one, it's easier to measure them in terms of logs, okay? 5 versus 6. And you also might recall from high school chemistry, pH stands for or represents how whether a liquid is an acid or a base. Same thing. Those are logarithmic scales. All right, so remember 7 is water. 7, anything above 7 is a base. Anything below 7 is an acid. So those numbers are actually exponents. They just say 6, 7, 8 because it's easier, but they're actually based on a logarithmic scale. So you've seen these before. So, all right, anyway, but here we just want to remind ourselves what a log actually is telling us. So here, for example, it's pretty clear. We know that y equals 10 to the 3rd power implies that y is 1,000. So we write that log base 10 of 1,000 is 3. So every log has to have a base. That determines the value of our result because that means that we are saying that 10 to the 3rd power is 1,000. Okay, all right, so hopefully, I know you studied this before, but it's probably been a while. You don't see them all the time. In fact, in many disciplines, we never see logs used, at least, well, some logs might show up, but a lot of them do not. So we have a couple of our examples, like log base 3 of 9 is 2, because 3 squared is 9. And then log base 2 of 8 is 3, because 2 cubed is 8. So why don't we do a few more of these? How about this one? Log base 5 of 25 is 2, because of the fact that 5 squared is 25. These statements both tell us the same thing. They're just basically equivalent. They're equivalent to each other. How about this one? Log. Let's see. Let me make one up. Log base 3 of 216 is 6 because 3 to the 6th is 216. Oh, no, it's not. Sorry, my fault. I did something wrong here. Six, not, hold on a second. 216. No, I just completely screwed it up. It should be 27. I don't know what I was doing. Let's try this. Just to keep it simple. All right, the ones you're most likely to see in practice are the logs with base 10. So here, log of 1,000, log base 10 of 1,000 is 4 because 10 to the 4th is 1,000. Oh, no, sorry, I meant 10,000. This is 10,000. Because 10 to the 4th is 10,000. All right. Now, there's a special name for log base 10. I think it's called a common log. Let me just confirm that. The common log. Okay. Because it is the one of the two you're most likely to see in practice. Now, your calculators, it depends on which one you have. If you've got the high-end ones, like the Texas Instruments scientific calculators, they'll have this built into them, but the lower-end ones, probably not so much. Now, sometimes, okay, so these are just more simple examples. The one I wanted to point your attention to is E. If log is to base E, that gets a special name. This one is called the natural log. And in fact, if you look at your calculator, most likely, if it has any predefined log functions, they're going to be natural log and log base 10. It's not going to have log 2 or 3 or 4 already built into it. It's either going to be log, natural log X, or log base 10, because those are the most common ones by a long shot. Like I was saying before, like with the Richter scale and the pH scale, those are both log 10s. The log X is actually, as we're going to see, related to e to the x. All right. In fact, let's see. Oh, here we go. Let's see. So basically, in the most general possible terms, if I write y equals log base b of x, what that implies is that b to the y power equals x. They're both alternative ways of expressing the same information. So think of it as basically solving for y, or x rather. So if I know this, I can figure out for x by using the reverse operation and turning that into b raised to the y power. Okay. So I did draw the picture here. Okay, good. The natural log. Oh, one interesting thing about logs is that the log of, for no matter what the base is, the log of 0 is undefined. That's an important result. Let's look at this on the next slide. It's not possible for any number to be raised to an exponent and come up with 0. So specifically here, this is the graph of y equals log x. And so you notice what's happening is that when x is 1, the log is 0. After that, the log is positive. But for any fractional value of x, the log is negative, but it never quite reaches 0. Okay, so the vertical axis is the asymptote of this function. All right, And then also note another special property. So I guess I'll summarize down here. Log to any base of 0 is undefined. I'll write that as infinity. And then log 1 is just 0. Doesn't matter what the base is. Those are always true because whatever b is, b to the 0th power is just 1. All right. Now down the road, we're going to compare this with, e to the x. I think it's coming up fairly soon. If you were to draw, let's do it now, just for the fun of it. All right, well, it's not the best drawing I've ever seen, but I hope you can see that they're essentially mirror images of each other. All right, so yes, they're closely related to each other because they are actually inverses of each other. So in other words, let's just quickly run through this. Y equals log x. Let's say that e to the log of x equals x. Log e to the x is x. So in other words, you can see they basically offset each other. Just like radical x squared is x and x squared radical is just x, because radical x and x squared are inverses. The same thing is happening here. E to the x and log x are inverses. And we just basically proved it right here. Okay. And that's why the graphs look like this. That's going to prove to be very helpful, by the way, especially if you find yourself in Calc 1. It'll help simplify a lot of very messy expressions. All right, so yes, common logs are the ones with base 10. I don't quite know where that name comes from, but natural logs, in fact, I'm not sure where this one comes from, but it's used so often that we call it natural log. I don't know who invented these names. In fact, maybe we can find out. Because they have similar derivatives. All right, that's something you won't see until Calc 1, unless if we get crazy ambitious and we crank through the material faster than usual, I might have time to introduce some extremely basic Calc concepts to you at the end of the course, just in case, especially if you're heading on to Calc 1. Well, we'll see how that goes, all right? That course spends a lot of time with a concept called the derivative, and we're not going to have time to do that here probably, or at least at best, I might be able to show you a few simple examples of it. All right, anyway, so let's just look now. These, again, this is what I was just alluding to earlier. The log to any base of 1 is 0. Oh, the log, I forgot this one. The log to any base of itself is 1. Okay, so in other words, the log of e is 1. The log to base 10 of 10 is just 1. All right, I hope that makes it's just common sense. The log to any base of b to the x is x. So in other words, the log of e to the x is x, as we've seen. Or the log of base 10 to the x is just x. Okay. Now we're going to introduce what are called the product rule. And so again, this will help us in a lot of very messy expressions. What you can do is if you have the log of a product, you can break it up into a sum of two logs. For example, it's demonstrated here, the log of 100 times 1,000, or you could, if you start out with a log of 100,000, by the way, which is what we have here, and you plug this into your calculator. You'll see that it is in fact 5, but let's prove it. We're going to break this up into the product of 100 times 1,000. And of course, as you know, 100 is 10 squared, 1,000 is 10 cubed. So I can rewrite it as log 10 of 10 squared plus log 10 of 10 cubed. And then these are easy to evaluate individually. So here we have 2 and 3, and they do in fact add up to 5. All right, so that was one of our rules. Remember this one. Log base b of b to the x is just x. So therefore, the log base 10 of 10 to the third is just 3. All right, it's as if the b's cancel each other out. They don't really, but you can think of it that way. And we're just left with x. So in other words, we just demonstrated with an example why this product rule works. Now here, for example, now, by the way, this isn't really necessary. Sometimes it can be very helpful. Also, sometimes this can help us simplify. Let me show you a case where it might simplify. Suppose you end up with something like this. Y equals log, natural log of x squared plus the natural log of 3. Well, we always like to simplify everything in math whenever possible. So you would say to yourself, wait a minute, this is the sum of 2 logs with the same base. Therefore, all I have to do is rewrite this as oh yeah, I think you'll agree that's a little bit nicer than having a sum like this. So sometimes a property like this is just used for simplification, but it's important to know that we can go in both directions. In other words, a sum becomes a product becomes a sum, as long as the logs have the same base. If they don't, there's nothing we can do. All right, so let's say as another example, I'll sneak this in here somewhere. If I had instead, let's say, y equals log base 10 of x and natural log of x squared, I can't add them. Okay, here we have base 10, here I have base e. These cannot be combined in any way because they're two different things. It's like I have an apple and an orange. I can't do anything with them. All right, now let's see. Like this one, for example, all we did is break it up. Now, normally you wouldn't do this unless it helps you arrive at a solution. But you might be tempted, like I said, to go the other direction. Log 2x plus log 3y, you might want to combine them and end up with log 6xy. Okay, so sometimes breaking this up like this isn't going to be particularly helpful, but it's important to understand that, that it means the same thing. Now, you might, in certain cases, certain types of equations can be more easily solved by applying this approach. So we don't have any examples just yet, but sometimes the purpose of you doing this is to make it easier to solve an equation. Okay, now here's the quotient rule. If the product of two values, the log of xy was the sum, the log of x over y is the difference. It's like here, here, for example, the log to base 10 of 10,000 over 100 is the log to base 10 of 10,000 minus log base 10 of 100, 4 minus 2, or just 2. Now, of course, this wasn't really necessary. You could have just done log base 10 of 100 is 2, but it's good to know that you can do this. Right, and again, sometimes this can help with simplification, especially these cases. Like this one, you can break this up, and you might, but probably you're more likely to do this. Take a messy expression like this and turn it or reduce it into a very nice ratio. Now, the next one is really one of the more interesting ones, the power rule. This will save us a lot of grief, that's for sure. Like, for example, what they're saying here is that when you have an exponent, you can convert that into a constant. So like, look how easy this is. The log of x squared equals 2 log x. Now, here's the reasoning behind that. Log x squared could be written as log of x times x, which based on the product rule is log x plus log x. Oh yeah, what do you know? It's 2 log x. So this is a simple case, and you can see why this has to be true. So in other words, instead of just memorizing a rule, we actually understand why this is happening. Same thing down here. Oh, you know what this is all about? Sometimes you see parentheses with logs. Like, for example, the log of x squared, we probably should use parentheses, but you don't have to. But let's say you have something like this. If the log applies to the entire expression, you should use the parentheses to make it crystal clear that you mean this and not something like this. Because that would mean log 3x squared plus 4. So if you really meant to do the log of the entire expression, you should use the parentheses. But in many cases, we don't bother. Like here, for example, log 3 or log x. So, you just have to be a little careful with those parentheses. All right. Now let's look at this one. Here's an interesting case. Because we're taking the log of a radical. So something like this, your best bet is probably to rewrite the square root of x as x raised to the 0.5 power. And now you can see that based on the power rule, I can just simply rewrite that as a half of log base 10 of x. Is that going to be helpful? It depends. It depends on the circumstances. It depends on what I'm trying to do. But again, the idea here is that we must be aware that this is true, because you never know when it might come in handy. I guess it's kind of like knowing how to use a wrench. You never know when you might need it. It's hard to say, but anyway, down here with a log of a cube root, we can rewrite this as the log of x to the 1/3, or in turn, 1/3 log base 10 of x. It means the same thing. All right, here's another interesting case. It's not that complicated. It's just that this time it's natural logs. And there's a second step here. See, I've broken up into a sum and a difference. Now, I thought that was kind of fun. The numerator is itself a product, and the denominator is here. And then I also rewrote this as 4 log x because of the power rule. So this ends up being 4 log x plus log y minus log 7. No, I thought that was kind of fun. All right, here's another case. Again, we've got fractions. So remember this, radical x is just x to the 1/2 power. Down here, by the way, here's an interesting one. This is the equivalent of x to the 2/3 power. So that's why we can rewrite as log of x to the 2/3 or 2/3 log x. Again, whether you choose to do this or not, it may help, it may not. All right, we've got a few more examples. Then we have a really interesting result. If you notice some of these logs, I mean, obviously we use log 10 and log base e quite often, but what if we have other logs to deal with? Let's say we end up with a result that gives us log base 3 or log base 5, and we find that very awkward to deal with. In principle, you can convert any logarithmic base into any other one with a certain rule that I'm about to show you. But first, we have one more example. Let's say these are, well, 3 different examples. Because log x4 equals 4 log x, you can go in both directions here. Okay. All right, here, for example, you notice what I've done. This became log base 3 of 2 to the 5th, which is log base 3 of 32. So, you know, not that it matters that much which you use, but it's important to be aware that they mean the same thing. Now look at this one. Now this one, it's really worth our while to look at it and see what we can do to simplify it. Look at this mess. This is equivalent to log base 10 of 100 squared, log base 10 of 10,000, and all of a sudden, now that really simplified nicely. 4. So this messy number on the left is just 4. I like that. It's just 4. Now, here's the formula that I was alluding to earlier. This will enable you to rewrite your log in any other base that you might find more convenient. All right, so let me show it to you, and then we'll do a few examples. The log of base b can be decomposed into the log of some other base n of x over the log to base n of b. So let's just say that I have a result like this. I could literally write this as natural log 27 over natural log 3. Now, if you go to your calculator, now, by the way, log base 3 of 27 is 3. So we can confirm this with the calculators. Log base 3 of 27 is 3. the natural log of 27 is approximately 3.29 log 3 is approximately 1.0986. If you divide those two out on your calculator, you'll discover that this is in fact 3. All right, even though I've rounded them a little bit, the actual ratio is in fact 3. Now you might say, well, why would I bother to do this? Well, think about this. Most calculators, if they do have logarithms, they either have log 10 or natural log. It's highly unlikely, unless it's a very advanced calculator, that it carries these other logs like log 3, log 6, log 8. So if you have something like this and you don't recognize that this is nothing but 3, let's say it's a very messy number, then you can rewrite it like this, and now suddenly you can use your calculator to come up with the correct value. So it's just a way of simplifying the results or converting them into something a little bit more convenient. Okay, or if maybe the ratio is what you actually have, you might want to convert it into the original expression on the left. It might just be more convenient. Now, here's another one. So for some reason, we've decided to convert this into log base 2. As long as you remember that this goes on top and this goes on the bottom, you can use any log base you want. Now, I don't find this particularly convenient, but you never know. In fact, you might even want to say, listen, if this is my result, this is a very messy result. I'd much rather express it as log 10 of 100 because I know that that's equal to 2. Over here, oh my God, your calculator may not even be able to do this. I think Excel can. I believe Excel has all of these built into it, but I'm not even sure then. Let's find out. Of course, Symbolab does. Oh, it does. All right. So the log of 100 base 2 is that number. The log of 10 base 2 is that number. The ratio of these two is going to be 2. All right, 2. Okay, perfect. So I might as well sneak those in there. 6.64 approximately over 3.32, which is 2. And of course, Symbolab can do anything like this. Let's find out. How does Symbolab treat logs? Let's see. Oh, here it is. If you want a log, you have to pick that log button. Let's say I'm interested in the log to base 10 of 1,000, which we already know is 3. But let's see what it does. 3. Yeah, because you see what they're doing is, I like this, what they've done. Let me just try that here. They're explaining it in a very interesting way. They're saying that what you should do is think about it this way. The log of 1,000, if you rewrite that as the log of 10 cubed, remember we said that it's almost as if these were canceling each other out, and you end up with 3. And so that's how they're recommending that you remember this. Okay, and they've also got a bunch of helpful rules here, which is kind of nice. All right, so now here's another one. This is the one you're more likely to run into. It's awfully, awfully helpful to be able to convert into natural logs. It really is. And so we'll do that here. Because like I have a really nice financial calculator here and it has natural log, it does not have base 10. I guess they figure if you need it, you can figure out how to convert it. All right, so, all right, anyway, now we're getting to the heavy duty stuff. Solving exponential and logarithmic functions. What if we don't just want to calculate logs, but we want to use them to solve equations? That's what this next part is all about. All right, so let's try this. So this is an important idea here. As long as b is not equal to 1, because then it's just 1 equals 1. The only way this equation can be true is if s equals t. So in other words, 10, okay, let's say 10 to the x equals 10 squared implies that x equals 2. So if you were working on an equation and this is where you end up, 10 to the x equals 10 squared, don't panic. All you have to do is say, well, wait a minute, the bases are the same. Therefore, these exponents must be equal to each other. And this is a very powerful result. It helps us with a lot of these very scary equations. All right, anyway, let's try some. Oh, here's an interesting one. 2 to the x minus 1 equals 2 to the 2x minus 4. Now, if you ran into this a little while ago, you would have said, oh my God, what am I supposed to do with this one? No problem. They both have a base of 2. So you can just set the exponents equal to each other and now solve for x. Look how easy it is. Great. So let's double check it. Is it true that 2 to the x minus 1 equals 2 to the 2x minus 4 when x equals 3? Two to the second equals 2 to the 6 minus 4. Oh, yeah. Whoops. It looks good, doesn't it? That's going to come in very, very handy. Very handy. But of course, it depends on they're both having the same base. Okay, so if you do something like this, that doesn't work. This requires a different technique. But we'll see later on that you can use logs to get what you need, but you can't solve by just simply equating the two exponents. All right, anyway, let's see, what else do we have here? Oh, I already did a double check. All right, whatever. How about this one? 2 to the 256 equals 4 to the x minus 5 power. Oh my God, what are we supposed to do now? We don't normally have our variable in the exponent, do we? Well, in this particular case, though, we might get lucky because 256 is actually 2 to the 8th power. And here's a hint, 4 equals 2 squared. So look what we're going to be able to do. I can replace 4 with 2 to the 2nd power. And you might recall that that implies that this is equal to 2 to the 2 times x minus 5 all right, just like if you had let's use a real number. Let's say if you had 10 squared raised to the 3rd power, that's 10 to the 6th. The same thing holds here. Now I'm all set because I can set these exponents equal to each other. And oh yeah, what do you know? It's 9. Wow, that took a lot of cleverness. So let's prove it. Let's go back and get the original results. Two to the 256 is 4 to the x minus 5 power. So we'll try 9. Well, what do you know? All right, so that was fun. What else can we do with logs to help save the day and make it easier to solve equations? Well, we can now, by the way, what we did there, we kind of pulled this one out of our hat because if you didn't recognize right off the bat that both of these can be rewritten as a common base of 2, you might not have gotten the right answer. There's other things you could have done, but this really made it simple. So we're going to try that in other cases. Like here, well, here it's pretty clear that you can do this. So what we did was we take this one and rewrite it as 3 to the 2x times 3 to the minus 1 power, or 3 to the 4x minus 7 equals 3 to the 2x minus 1. Now we're all set. This is easy. All right. Didn't look easy, did it? No. So now you just set them equal to each other and you have x equals 3. And let's confirm it, because it's always good practice. Let's see if it's true. 3 to the 4x plus 7 or minus 7 equals 3 to the 2x over 3 when x equals 3. And so 3 to the 5th. Now here, if you write this as 3 to the 1st, you can see that this is clearly 3 to the 5th, and you're all set. All right, is there another set of fun techniques we can use? Yes. What about cases where we cannot find a common base? Then we're going to use logarithms to help. Okay. Now, keep in mind, when you solve any kind of an equation, anything you do to the left-hand side, if you match it on the right-hand side, you will not affect the answer. So you can literally apply any mathematical operation to both sides of the same equation and come up with your results. And that includes taking logs of both sides. And that's what we're going to do here. Like this one. Now remember when we had 256 equals 4 to some power, that one we were able to create common bases. We can't do that here. So let's try this instead. Let's take the natural log of both sides. Now, let's try that. And by the way, this is where all those wonderful properties will start to really pay for themselves. So you're probably saying, well, what's going on here? How is this helping us? Well, now remember, the log of x to the a power is a log x. So therefore, what I can do is rewrite this first one as x plus 2 times log 5. This is the base. Over here, I can write this as x times log 4. And now here I can just distribute x plus 2 over log 5. And over here I have x equals x log 4. Now, keep in mind, I'm trying to solve for x. So I'm going to subtract this from both sides. I'm trying to isolate the x in this equation. And then I can start to get more. I can simplify this by factoring out a common x, which I have in both terms. All right, let me just leave it there for a second so you can catch up. All right, so now I'm going to use a little algebra. Actually, this is the last statement is right here. I just repeated it. I'm going to factor out a common x and divide, and simplify it by rewriting it as a ratio, although that's not absolutely necessary. It might speed things up a little. And then all I have to do is divide both sides by log 5/4. Okay, and that's pretty straightforward. Now, the reason why this is helping me is because even though it's a very messy answer, I could go to my calculator and find the exact value of the expression. So in other words, I end up with this catastrophe. Yes, and it looks frightening, but I have my answer. Now, if you're really dying to know, the numerator is 3.21888. The denominator is about 0.22314. And so that ratio is about 14.43. So if you're solving an equation, let's say this is the optimal price to charge for your product, or you're running a business and you discover that this relationship holds between, let's say, the cost of production and the revenues. And so you set them equal to each other, and there you go. That's our break-even point then. Okay, so if this represents costs on the left and revenues on the right, then what I've just solved for is your break-even point. Which means if I sell 14.43 units, I'll break even. All right, so that's one way we can solve for equations when they don't have a common base, and it's not realistic to think we can get one. But there's more things we can do still with these wonderful properties. Now, like, look at this one. These both have a common base. Okay, so that gives us a hint. Oh, that's right. Remember, the log of base b of x, y is log b of x plus log b of y, which means if I start here, I can convert to this. And that's exactly what I'm going to do here. All of this will be consolidated into log base 2 of 2 times 3x minus 5. So I've got to this point now, and you're probably wondering, well, now what do I do? Good question. It appears that we're stuck, but we're never stuck. We always have a technique that we can use to come up with the correct solution. Now, this requires us to go back and revisit the actual definition of a log. So remember, let's say I had the log of base b okay, now, or how about this one? So what I can do is the following. This expression implies, based on what you're seeing here, that 2 to the third power equals 6x minus 10. Now, we've done similar ones over here on the right. It's just that this one is more complicated. But because the log of base 2 of this 6x minus 10 is 3, that means that 2 to the third power is equal to this number. And that means we can turn around and solve for this directly using normal algebra. Okay. So this one was pretty challenging because, yes, again, you have to go back and remind yourself what a log actually means. So like if you had log 10 of 1,000, this equals 3, based on the logic above, because 10 cubed equals 1,000. Same thing here. This implies that 2 cubed is 6x minus 10, and then we can go ahead and solve for x very quickly and easily. Yeah, that's pretty cool. Look at that. It looked to here like you were stuck, but you're not. Okay, so 2 cubed equals 6x minus 10, and of course that means 8 equals 6x minus 10, and when we're done, x equals 3. Now let's do the double check. We started out with log base 2 of 2 plus log base 2 of 3x minus 5 equals 3. So 3 is x. So this is the same thing as log 2 times 4. And because we know that this implies that 2 cubed is 8, that means we've done this correctly. All right, well, here's another one that you might find interesting. Based on the same logic, we're going to use the properties, and then we're going to wind up with our result. Let me give you a minute to catch up. So you don't have to always do these double checks. I just think it's a good idea to get some practice and make sure you haven't made any mistakes. So let's say you had this kind of thing. So you start and say, all right, well, I can consolidate the constants on the right. I can divide out that 2. And so I'm here. What now? Okay, well, I can take the log of both sides of an equation. Without affecting the results, of course. We already knew this, okay? So doesn't that mean that I can do the following? I can raise both sides of the equation to an exponent using the same base. Oh, I see there's a chat here. I hope I haven't been ignoring you. This is chapter 4. Oh, okay, that just went in. I hate it when I don't notice the chats. This is all chapter 4 still. 5 is where we start to introduce trig. So you'll know when we're in chapter 5, believe me. I don't know how you feel about trig. A lot of people hate it. A lot of people like it. You might, but you've definitely seen it before, but I'm pretty sure that you've started to forget. Yeah, I bet most of you will say the same thing. I don't find it particularly useful either, but that's only because my background is really more in economics, where we only, economics is a discipline that's very mathematical, but ultimately we only care about things that are useful. Trig, yes, it's hard, but we're going to try to we're going to try to explain it a little differently this time. All right. We're going to try to maybe give you more of a big picture. Instead, in high school, there's a tendency to obsess over memorizing details. We're going to see a very interesting setup that will enable you to find your results without too much pain. And there's actually videos to help us with this too. Well, I can't explain it to you right now in English. When you'll see. All right. It involves a very special circle, and we'll quickly review our knowledge of geometry as we go along. But we only need a circle and a triangle to help us generate essentially all the results that we need in trigonometry. But okay, so we'll save that for later. Don't worry, I don't want to be too mysterious about this. But anyway, so yes, we have the right to do this. I can raise both sides of the equation to an exponent using the same base. So actually, you know what, let me see if I can come up with an example of that. If I said, for example, that x equals 3, let's see, what can I do with this one? Remember before we said that if we have the same base, this is what I'm alluding to. So in other words, if you had an equation like this, s equals t, you can rewrite it as b to the s equals b to the t if you need to for some strange reason. Well, actually, sometimes we're going to need to do this. So in other words, raising both sides of an equation to the same base is allowed too. All right. In other words, again, as always, if I apply the same operation to both sides of an equation, I will not affect the results. So why am I mentioning that? Because natural log x of 2 equals 2. Watch what I can do. If I rewrite this as e to the log x equals e squared, I haven't changed anything. But you might recall one of the properties we learned earlier is that e to the log x is just x. So all of a sudden, I've got x equals e squared. And then I can figure out in my calculator. So the original equation, log x equals 2, is the same thing as saying that x equals e squared. And of course, e squared in your calculator, you'll see, is simply equal to 7.389. So when you come to this point, you might say, oh, I'm done. I can't do anything more. No. Now you have to make a very clever choice, but you recognize that it's because log is base e. Let me rewrite this as log e. So by writing e to the log x, log ex, this is equivalent to simply x equals e squared. But it might be easier to remember this. But they both mean the same thing. So these are the same. And if you're not sure, go to your calculator and type log 7.389. It'll come back with 2. Approximately, because you're rounding it. That's our double check. Wow, that was interesting. So, all right. Anyway, I guess we better stop for a few minutes. It is already 10 o'clock. We're going to keep going with some. There's almost no more. There's like one or two more examples, and then we can dive into our dreaded trigonometry discussion. I guess we have plenty of time after all. I wasn't sure about that. First, we'll review our basic ideas, and then we'll start diving into the more complex notions. And so I'm hoping it'll come back to you fairly quickly, and maybe this time around you'll have a more pleasant experience with it. But it's not and it's really nobody's favorite topic. Let's put it that way. Although I must say, I preferred it to geometry when I was in high school. I really did not care for geometry at all. I liked it better, but it's not saying much. So but anyway, as you get further into math, though, it's awfully important to be on top of those trig functions because you do run into them quite a bit, especially in Calc 1 and 2. But in the real world, you normally only use trig functions in certain disciplines like engineering. And for business applications, it doesn't happen very often. So that's where you're headed. You're not going to have to worry excessively about trig functions. All right, so we'll stop for a bit. We'll come back and do a couple more examples of what we're doing, and then we'll get into our trig functions. Okay? All right, let's do this. All right, so we're almost done with this section. What else do we have? Oh, here's another one. Now, this again, because you're starting with a natural log, you're going to convert this eventually to E. So we started out very basically dividing both sides by 2. And again, when you have a natural log like this, if you have log x equals, let's say, it doesn't matter, 10. E to the log x equals e to the 10 implies that x equals 10. It's just that simple. Sorry, e to the 10. And you're done. Unless you need the exact value of e to the 10th. So here we're doing a little algebra first to get it into the form log 6x equals 7/2, which again implies that e to the log 6x equals e to the 7/2. And then remember too that e to the log x is just x. So this reduces to 6x equals e to the 7/2. And then we just divide by the 1/6 and we're all set. All right, so now there's one more here. I'm just going to combine some of these properties that we've been using just to make sure that we can get this. Oh, all right, so here's an example. You'll like this one. It combines a lot of the concepts we've just been looking at. So now look at this. And first glance, it looks like a catastrophe that there's no way we're ever going to solve for x. But we notice that they all have a common base of 2. So therefore, these two on the left can be consolidated into a single ratio. Because remember, the log, or any log, let's say to base b of x over y equals the log to base b of x minus the log to base b of y. And so here we're going to take that difference and turn it into a ratio. All right, so the left-hand side is converted to a ratio. The right-hand side, we can leave it alone. Now, both of these are the same log, aren't they? So that means, remember, we had log to any base of x. If we have something like this, this implies that x equals y. All right, so in other words, we know that both sides are the log. So in other words, if you had started out with x equals y and you took the log of both sides, you'd end up with this. So what we're doing is working it backwards. We already have a common log base. So therefore, we can simply rewrite it as 3x minus 2 over 2 equals x plus 4. Okay, so remember, we had previously log 2. So we can basically work this backwards and just say that, well, since they have the same base, that means that 3x minus 2 over 2 equals x plus 4. And then the rest is just straight ahead algebra. And we end up with x equals 10. All right, so that's 4. We're all done with it now. And so that means it's time. I know you might be dreading this, but it's time for chapter 5, which is our overview of trig functions. Now, it's not a terribly long chapter. Oh, by the way, you know what? Well, you're still working on the midterm, so maybe we can save this. But at some point, we're going to do a bunch of problems in chapter 4. Maybe we'll hang on to that until next week. I don't want it to be due. Well, on the other hand, your exam is due tonight. So I'll tell you what, why don't we agree that next week we'll go over the chapter 4 problem set. Okay, so in the meantime, let's start 5. Yeah, I know you're not looking forward to this, but that's okay. So we have trig functions. Now, these are the 6 basic trig functions, which are often abbreviated sine, cosine, tangent, cotangent, secant, and cosecant. Whoops. Now, you may have been taught a very interesting mnemonic device to help you remember these, at least the first 3. All right, so exactly what do these tell us? Well, let's say you have a triangle, a right triangle. Let's see. Let's make it 30, 60, 90. So that's the symbol for the right angle at 90 degrees. Let's say this is 60 and this is 30. And you might recall this symbol means 60 degrees. And so the classic example of this is the 1, 2, radical 3 right triangle. And you might recall the Pythagorean theorem. A squared plus B squared equals C squared. So if you think of this as your A and your B, and this is your C, you can see that it works. 1 squared plus radical 3 squared equals 2 squared. 1 plus 3 equals 4. What about the trig functions then? What are they all about? Well, the trig functions are ratios. And they're expressed in terms of 3 concepts. Let's see. Let me draw another picture here. Let's say this is your angle. This is x degrees. And by the way, don't forget that a triangle contains 180 degrees. A right triangle, well, if you want to work in the midterm now, you can go ahead and watch the recording later on. That's fine. Not a problem. But yeah, so anyway, triangle contains 180 degrees. So that implies that this angle up here must combine with x equals 90. So this would be 90 minus x. But what I'm trying to get at here is that relative to angle x, this side would be the adjacent side. This would be O, or opposite. And this is H, the hypotenuse. So all the definitions of these trig functions are in terms of O, H, and A. Opposite, adjacent, and hypotenuse. So if we stick with the, well, in this case, we have the exact values, but just in the general most possible terms, we have this mnemonic device you might remember. And if you've never seen this before, well, you'll be in for quite a surprise. It's hard to imagine anyone remembering this, but does it look familiar to anyone? What is that? What is all of that? Okay, Fernando, you remember this, and it's called?
SOHCAHTOA.
That's right. And what does it mean?
It's pretty much, if I'm not mistaken, I think that's like every single like part of like the 6, like, or the tangent. I mean, I'm sorry, like, you know, sine, cosine, and tangent.
Yes. So in other words, it's there to remind you sine equals opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. All right. Does that ring a bell to everyone? Now, the other 3 that we introduced earlier, remember there's 6 altogether, 6 trig functions. These 3 are all derived from the first 3, so they're not really anything new. And here's how they're related to each other. The cotangent, which is, oh, by the way, the abbreviation for cotangent is COT. Yeah, I do have it here. All right, the cotangent is the inverse of the tangent. These you just have to remember. The SOHCAHTOA will give us the first three. The other three depend on the first three. So in other words, the inverse of the cosine is the secant. And then the cosecant is the inverse of the sine. And there you go. You've got all 6 of them. So with that in place, you can, in principle, calculate any of these measures from any triangle you happen to have, such as the one we were looking at before, this 30s, this one right here, which is often called a 30, 60, 90 right triangle. All right, so you could go through in principle and say, all right, well, I can easily calculate some of these measures. Let's see what we can do here. Maybe we'll get some practice right now. No, I'll just draw it all over again. That's fine. So for example, the cosine, well, let's try the sine. Let's start with the sine. The sine of 30 degrees, remember, sine is OH. So compared to 30 degrees, the opposite is 1. The hypotenuse is radical 3. Okay. Now, you don't normally leave radicals in the denominator, so here's what we're going to do. We're going to rewrite this as 1 over radical 3 times radical 3 over 3 yes. So you end up with this. And that's how they're done. So it's really, in that sense, they're not that difficult. If you wanted, yes, Fernando.
Sorry, I didn't mean to cut you off, but right after you multiplied it by radical 3 over radical 3, since 1 over 3, the denominator for radical 3 multiplies with the other denominator radical 3, it turns back into a 3.
Yes, exactly. That's the purpose of doing this, to turn the denominator into a not a square root. In other words, a rational number. This is just done by convention. It's not that this was wrong, but normally in math, we try to avoid having radicals in the denominator. It's just like if I had 2 over 4 here, I would have converted it into 1/2. It's the same principle. Yes, go ahead.
So then couldn't we like multiply 1 over radical 3 by itself and would have gotten like 1 over 3?
No, because then you're changing the value. You see, the reason why you're allowed to get away with this is because radical 3 over radical 3 is just 1. Okay, so yeah, if you start multiplying it by something else, you'll change the answer. All right, so yeah, you're not allowed to do that. You have to multiply it by 1, but the way you choose the 1 can be anything you want. All right, let's do another one. The cosine is 60. A over H. Now, with respect to 60, 60 is up here in the upper left-hand corner. So from its perspective, the adjacent is 1. And the hypotenuse, well, what do you know? They're the same. It happens. Sorry. It's radical 3 over 3. Okay. How about the while we're at it, the cosecant of 30. Remember, cosecant is the inverse of sine. So you'll just have, sorry, radical 3 over 1, which is just radical 3. So this is how you can take a triangle like this, and you can figure out whatever you need based on the sides. Okay. And the reason why these work is because of the Pythagorean theorem. This is what defines the relationship between the squares of the two sides and the square of the hypotenuse. Okay, now, what else do we need to review? I don't know. Let's go on and see what we've got here. An angle is defined as the relationship between two rays. Oh, now you remember this. A ray has a single starting point and then it goes on forever. This is a ray. A line goes on forever in both directions. Okay, you might have forgotten this. The word ray implies that it has a specific starting point, but after that, it goes on forever. So an angle is formally defined as the relationship between two rays that have the same endpoint. In other words, let's say my rays look like this. Those are two rays. This is the angle between them. Whatever that is, it could be anything. Oh, by the way, also, I mentioned here the triangle has 360 degrees. We also want to remind ourselves that a circle contains 360 degrees. In fact, it's because of this that we have hours and minutes and seconds defined the way they are. You notice how you might think, why didn't we have like 10 hours in a day and 10 minutes to an hour and that kind of thing? No, because the clock is a circle and it's divided into 1 hour at a time. Each hour would represent 15 degrees. And so the circle has 360. And so our time is all defined in terms of this base 60, actually, which was invented by the Babylonians. Yep, it's too late to do anything about it now. Even in the metric system, this is all the same. All right, now here's a perfect example of that. By the way, you might recognize this Greek letter. Now, every year when I do this class, I always ask this, and I find that most people have forgotten this one. Who remembers which Greek letter this is? Fernando?
I remember what it looks like. I just forgot the name of it.
Yeah. See, now you're not going to be able to Google that because it's a symbol. You have to actually remember this. So, you know what you could do though? Why don't you Google a chart of the Greek letters? I'll give you a hint. It starts with a T.
Theta.
That's it. Theta, our old friend theta. Now in math, certain Greek letters tend to be used for the same thing over and over again. For example, our old friend pi, which is usually used to represent 3.141, blah, blah, blah. Okay, you saw that a million times in geometry class. Delta, which is used to represent a change in something. And theta, which is usually used to represent an angle. It doesn't have to be, but that's a pretty common use of it. Theta is almost invariably used as an angle. So if you see that word theta, you know what they're talking about. Nobody expects you to memorize the whole Greek alphabet, but there's certain ones that you really need to be very familiar with. Or like this one. This is the uppercase sigma, and it's used to represent summation. You're adding something together. Okay. And then there's some that you hardly ever see, like this is Z, which you only usually see in physics or incredibly advanced math books. There's all kinds of wacky Greek letters that we may not see very often. All right, now, So the two rays have a common starting point. What they're trying to illustrate here is that you have to imagine that they both have this common starting point, but then they go off in different directions. And they do go on forever, but they start here. And so this represents the angle between them. And now we can also think in terms of an initial side and a terminal side. So in other words, this implies that we're moving from one to the other. Now, this will come in handy later on. You'll see. Well, don't believe me, this will be important. So if we're starting on one side and moving to the other, the first one is the initial side, the second is the terminal side. The word vertex means that this is the point where they both started. Now, this is all just terminology. You don't have to memorize a lot of this stuff, but it's good if you see it, you'll recognize what these words mean. So we can think of the angle is the amount of rotation from the initial side to the terminal side. In other words, imagine that you're moving this, or it's like, you could think of this as like a big minute hand. Now, of course, it's going the wrong way, but imagine that clocks were designed to go the other direction. The minute hand goes up to here. The amount of movement that's required to reach this new side is called the angle. And each degree is 1/360th of an entire circle. That's how we think about it. In other words, what proportion of an entire circle does this represent? Whereas a circle would mean we come all the way back to the start. So let's say this represents 1/5 of the total. That would imply that that was 360 divided by 5, which is 72 degrees. So you have to think of the angle as what proportion of a circle are we covering when we go from one side to the other, or from one ray to the next. The degrees, number of degrees, is the proportion of a full circle. Because if you keep moving this around, of course, imagine, like I said, this is a minute hand. It's going the opposite direction from what we're used to, but still, eventually it'll come back to its starting point and it will form a complete circle. Now, that raises a very interesting historical question. When you stop and think about it, you know that standard clocks are set up to go in this direction. This is how we define the word clockwise. The opposite would mean you're going from, let's say, here to here. And this is called counterclockwise, or some countries, they call it anti-clockwise. Now, when you look at them, you can see that we ended up with this method right here, but there's no reason why we couldn't have had the opposite. In other words, the minute hand could have just as easily been designed to go around the opposite direction. So there's a very important historical reason why we ended up with the first one as our definition of clockwise. Now, in order to come up with the reasoning behind this, you have to ask yourself, what exactly did we have before there were clocks to tell time? Did we just not care? Or, you know, clocks haven't been around all that long compared to human history. What if you were in Rome in 1000 BC? How did you tell what time it was? Yes, go ahead, Fernando.
Actually, never mind. I thought of something else, but that was a different time period. Never mind.
Let me see if I can find a picture of this amazing device. Oh my God. Here we go. What is this thing called?
That's exactly what I was thinking about, but I thought there was.
But you forgot the name. It's a sundial. And so what we have to do is we look at the sun casts a shadow on the sundial, and that's how we know what time it is. The shadow is in the position that our minute and hour hands would be on a modern clock. But here's the interesting part. As the day wears on with a, I like this picture. You know what I'm gonna, let me see if I could, I think I can steal this for my slide. Okay, just because I think it'll make it more easy to see what I'm doing. And I'm not the best artist in the world either. So, I mean, it's kind of tilted on its side, but you can see it starts up here and you can see the numbers, the Roman numerals are moving down in this direction. So why is that happening? Okay, you notice how here's 1, 2, 3, 4, etc., all the way back to 12. The hours are going in this direction. Why? Because in the northern hemisphere, the sun's shadow is moving in a clockwise direction. So let's say it's 3 o'clock if the shadow is here. It's 5 o'clock if the shadow is here. So the shadow of the sun is moving in a clockwise direction. And that's why the earliest clocks, of course, would have used this motion to represent the passage of time, because that's what we were used to. Now, here's another interesting detail. These clocks were invented in the northern hemisphere. If you were south of the equator, hard to believe, and this is absolutely true, it works backwards. Okay, so in other words, in the northern hemisphere, by which I mean above the equator, the sun's shadow moves in a clockwise direction. In the southern hemisphere, the sun's shadow moves in a counterclockwise direction. So had sundials been invented in the southern hemisphere, our clocks would all be going the opposite direction that they are now. How do you like that? So whoever invented the sundials lived north of the equator, and so because of that, this direction came to be known as clockwise. And in fact, you know, if you ever look very carefully, if you look the way water circles down a drain in the northern hemisphere, it's going clockwise. In the southern hemisphere, it's going the other direction. So because the rotation of the earth is coming from the opposite side, so a lot of these things are reversed in the north and the south. Interesting. How do you like that? So the next time you're in the southern hemisphere, take a good hard look at the water going down the sink. You'll see that it is in fact going in a counterclockwise direction. Wow, that was interesting. Now here's another fun fact. Clocks, I don't know. Let's see if we can find roughly when clocks started being used. I think it was probably during the Middle Ages. 14th century. Okay, that sounds about right. The 1300s, when it became possible to build mechanical devices like this. The technology didn't exist before that, so we stuck with the sun. But man, there's some cool clocks in here, huh? Look at that. There's our sundial. Woo-hoo-hoo. Anyway, now here's an interesting detail. The earliest clocks only contained an hour hand. The minute hand didn't really get started. In fact, let me confirm the year. I'm thinking the late 19th century. Oh, that far back. Oh my God. But a lot of clocks did not have, even though they may have invented it, a lot of clocks didn't really commonly have a minute hand until much later. Now, at least in the United States, there was a very good reason why we suddenly started needing a minute hand. And when you think about it, I mean, throughout most of human history, most people worked in agriculture. I mean, that's just the reality. We needed to spend almost all of our time growing food in order to survive. So if you're a farmer, I mean, you know, you're planting your crops, you need the sunlight to do your work. But I mean, really, does it really matter if it's 10 after 1 or a quarter after 1? No, of course not. Not really. How does it matter? You're just going to be out there planting anyway. The thing that really made it necessary in the United States to have minutes was the railroads. So if you're going to get on a train, you have to know exactly what minute it is. Otherwise, you're going to miss your train. So when the railroads started being developed in the after the Civil War, it started to matter a great deal if it was 10 after 1 or a quarter after 1. So that's roughly when the habit of having a minute hand got started. Prior to that, you know, we didn't need to be quite that accurate. In fact, if you look at a sundial, it's going to be hard to see the difference between quarter after and 20 after. Let me put it that way, because it didn't matter. All right, what difference did it make? But then all of a sudden, technology makes it necessary to know exactly what minute it is. So that's when that got started. Okay, and then of course they also then eventually add the second hand. That one, I don't know. I've never heard of anything that needed to be timed right down to the second, but you never know. It's kind of nice to have that information. Now, of course, in this day and age, everybody's using digital clocks. I hope that they're teaching kids in school how to use the traditional clocks. We don't want to lose that knowledge. Even though it's a little trickier, you know, it's an important skill to have. But anyway, all right, so enough of that fun stuff. I just wanted to point that out as we're talking about angles anyway. So let's see, where were we? Oh, here we go. Now, the standard position, as it's so called, is right here. In other words, we're going to start on the x-axis. So you might recall from high school that this is referred to as the first quadrant. This is called the second quadrant. This is the third quadrant. And this is the fourth quadrant. Okay, they're called that, just to break it up, the XY coordinate system into 4 equal regions. Many applications, we only stick with the first quadrant because we're guaranteed that X and Y are positive. So if we're dealing with, let's say, profits for a corporation, we'd only be interested in the first quadrant. All right, so the angle, again, tells us how far do we have to move from the initial to the terminal side relative to going all the way around the entire circle. So you might also recall that moving exactly from one region to the next is, let's see, let me draw my own little picture here. If you go to here, this is exactly 90 degrees. And we often draw it with that little rectangle. Actually, let me just write 90. Ah, 90 degrees. If I go all the way over here, that brings me up to 180. To come all the way down to here, is 270, and then come all the way back to the top is 360. So each quadrant has 90 degrees in it. 90, because that's 1 out of 4. In other words, if the entire circle is 360 degrees, each quadrant represents 90 degrees. So, all right, here we go. So this is coming from the book. That's 90 degrees, which is pretty straightforward. Now, here's where I'm going to frighten you. What if we decide to go the opposite direction? What if we say, you know what, we're tired of going counterclockwise? What happens if we go clockwise? Like here, for example, this is defined as a negative angle. Yes, you're going 135 degrees, but you're going the wrong way. And so this is referred to as a negative angle, which interestingly enough is the same. Now imagine that you're like driving and you and your friend are driving in opposite directions. And so I'm going this way. We decided to meet up here because there's a nice little restaurant there that we want to eat at. I'm going the traditional counterclockwise method. And altogether, you see, I've gone 90, 180, and then another 45. Going from this direction, this is defined as 225 degrees because it's all the way through the first two quadrants, halfway into the third quadrant. So what that means then is that 225 is negative 135. In other words, they both mean the same thing because we end up at the same place. Oh, now this is getting a little scary. I don't know if you were ever exposed to negative angles in high school. It just means you're going the opposite direction. But keep in mind, they're not the same number, are they? No. They represent the same position because we're both here. It's just that I took the long path. I drove all the way this direction, and the other guy took the shortcut, went the opposite way, and he ended up there at the same place, but he only went through 1.5 quadrants to get there. So to separate these two, we're going to call the clockwise a negative angle, and counterclockwise will be positive. Now, I want to point out one important detail here. If you ignore the signs, in other words, you take the absolute values, what's going to happen is that these will always add up to 360 degrees. So that's how you can help yourself remember how this relationship works. You need two angles whose absolute values add up to 360. Okay, so just keep in mind, they both represent the same information because they mean we've moved to the same location. All right, so let me show you another one. This one's a little bit more straightforward. Let's say I go just to here. And somebody else, I'm meeting up with somebody again. They're coming, we're going to meet at a restaurant. And but we're going in opposite directions.
I'll catch you.
This would be defined as minus 180 because I'm going halfway around the circle, but in the opposite direction. So, and you notice the absolute values do in fact add up to 360 as they must. So that means these equal each other. Okay, Now, by the way, just for the fun of it, I just want to ask you this question, if you remember this. What happens if we have a fraction of a degree? Well, each degree is equivalent to 60 what we call seconds. And each second is equal to 60 minutes. I'm sorry, each degree is 60 minutes. So there's, in this sense, it works just like the clock. And each second is, I'm sorry, see, I completely screwed this up. Each degree is 60 minutes, and each minute, as you can imagine, is 60 seconds. And we have symbols for these. This symbol means 1 degree. This symbol is 1 minute. And this symbol is 1 second. So we can have fractional degrees. And what I'll show you an example when this might be useful. What if I asked you the following question? Here we are in roughly New York State, you know, purchases in New York State, not very far upstate. What is our latitude in purchase? Now, you might recall from your high school study, or even younger than that, how latitude and longitude work. The equator is 0 degrees latitude. The prime meridian is 0 degrees longitude. All right, so here's the equator, cuts the Earth in half. This is the prime meridian. Oh God, I just, okay, so here, where's up here somewhere?
What?
So why don't we look up our latitude? And it's going to be slightly over 40 degrees north. But let's go see the exact value. So watch this. What is the latitude of Purchase, New York? Oops, sorry, I spelled it wrong. Now look at how it's written. What do you see there? Well, those are coordinates that are meant to indicate this first one means 41 degrees, 4 minutes, and 0 seconds north. That is our latitude. Our longitude is 73 degrees, 71 minutes, and 44 seconds west. Now, when they say west, they mean west of the prime meridian, which is in Greenwich, England. So the prime meridian cuts through the town of Greenwich in England. And in fact, all of the time zones are defined with respect to what's called Greenwich Mean Time. So if you look up, like right now, New York time is, I believe, 6 hours ahead of Greenwich. So we're located somewhere around.
Oh my God, I'm so fucked. I'm so fucked. Travis, before
All right, we're sorry to hear that. It's so sad when people say bad things when they don't realize they're on the microphone, but you know what, we'll do our best to keep it quiet here. So anyway, so we're right about here. So now I'm sure at some point in your life you've been exposed to all these ideas, but I just wanted you to see it because we're talking about angles. Now the notation they're using is a little different. Some will put those symbols, minutes and seconds, but here they've written it slightly differently. Like I said, the first part is the degrees, minutes, and seconds. Okay. And so west means west of Greenwich, England. North means north of the equator. So you can find exactly where we are with the GPS system. I don't think GPSs actually tell you the latitude, or they probably could if they really wanted to. But a lot of people simply wouldn't know what that meant, and so they probably just don't bother. So now what's interesting about these longitude and latitude lines is sometimes if you might wonder, well, where are we compared to other cities in the world? Our latitude line is roughly comparable to Madrid, which you might surprise you given how warm it is there. But anyway, so this is how a latitude and longitude work. So if you're ever wondering where you are, you could use this. So, by the way, why is the prime meridian in Greenwich? What's so special about Greenwich? Because they chose to pass it through the Royal Observatory in Greenwich, which was the home of Sir Isaac Newton, who invented all of this stuff. So that's why it was chosen, that location. In fact, if you go over there, and I've done this myself. If you go to, here it is. If you actually find yourself in Greenwich, look at this. There's this enormous statue there. This big line is actually there on the ground. You can step on this thing, and a lot of people do that. They want to get a picture of themselves simultaneously standing in the Western and the Eastern hemisphere. It's pretty cool. Like this little kid, he knows what's going on here. He knows that he's straddling the East and the West. It's kind of fun. Everybody, it's like the bull in New York City. Everybody has to come and sit on it. All right. Well, anyway, so that's enough background with angles. But just be aware that you can break an angle up, a degree rather, into minutes and seconds if you need to, just like the clock. So the degrees correspond to hours. And then we have minutes and seconds. All right. Well, that was kind of a fun review of all the science you've ever learned. No, you've had lots more, but does this bring back a flood of pleasant memories to think about this stuff? Oh, I'm afraid that means no, you're not remembering this with fondness. Well, that's kind of unfortunate. This stuff is kind of fun. But this is how the time zones are defined with respect to longitude. Okay. All right. Well, anyway, so let's get back to this. So you can see in this chart, they're showing you how to map out 0 degrees means you simply stay on the horizontal axis. 90 degrees means you move over to the vertical axis. 180 you go back to the horizontal axis again. And then 270 means you go 3/4 of the way through. And 360 would mean the same thing as 0, which I forgot to write that down. In addition to the negatives, let me do one more graph for you. If I were to go all the way around and come back to where I started from, that could be defined as 360, but it could also be defined as 0, because it both means the same thing. You're right back where you started from. All right, so just remember 360 and 0 mean the same thing. Now, what that implies then is that if, let's say, I do something like this, going around to 45 and going all the way around and then back, 45 degrees and 405 mean the same thing, because to go all the way in the circle plus another 45 degrees brings me here. But if I just go 45 degrees, I end up here. So these are equal to each other because the difference is 360. So what this really means is that no matter what angle we have, any angle inside that range from 0 to 360 is equivalent to many other angles that are either larger than 360 or else they are negative. But there's only then 360 unique degrees then. The others, anything else you might run into, is a function of what we're seeing here. And so, oh, by the way, there's always terminology associated with any discipline. Here's another one. I don't know why this is important, but formally, these angles are called quadrantal angles. Now, you don't have to memorize that, but I wanted to throw it in there. I guess it's because of this quad. Okay. So just remember that if you see that word, it just means it's either 0, 90, 180, 270, or 360. Now, here's something that you may remember being a major nuisance. For certain applications, the choice of units, degrees as a choice of units is not the most convenient thing in the world. We have this alternative way of expressing angles, which is called radians. Now, you might not think so, but for some applications, it's easier to think about radians than degrees. Now, I personally don't think so, but yes, we have to remember this. So the way this works is that 2 pi radians is the same thing as 360 degrees. So a single radian is approximately 57.3 degrees. Yes, like I said, for certain types of applications, it's easier to use the radians than the degrees. So, you know, as long as you remember this detail, you shouldn't have a problem. So what that means is, for example, pi radians obviously then must be 180 degrees. Okay, that kind of thing. Pi over 2 radians would be 90 degrees, et cetera, et cetera. Okay, so just remember the starting point is 2 pi radians is 360. The rest will fall right into place. Now, your calculator is not going to have radians in it. It's always, I believe your calculators will all do degrees, but you never know. And here's a little chart I put together just for your convenience. And if you need more of them, like for example, given this chart, 3/4, 3/4 pi radians would be 3 times 45 or 135 degrees. Or like here, pi over 12 radians would clearly be 15 degrees. All right, so we'll revisit this idea later on. It's enough now to remember how this relationship works. All right, now more terminology. Remember, we defined before an angle as the relationship or the rotation between an initial side and a terminal side. And we also saw that going counterclockwise by 90, let's look at this case. Going counterclockwise by 225 is equivalent to going clockwise by 135 degrees. So these two, which we know represent the same thing, are formally known as coterminal angles because they have the same terminal side. It just means they're the same thing. You can call them coterminal, but it means that they're the same angle because they end up at the same point. They both wound up on this ray. All right, how do you find them? Well, here, for example, is a case where we go counterclockwise by 140 degrees. And again, imagine yourself meeting up with somebody at this restaurant right here. If I go this way, I'm going 140 degrees counterclockwise. The other driver might find it easier to go 220 degrees clockwise. And if you notice, once again, the absolute values have to add up to 360. That's how you know you haven't made a mistake. Okay, these are then defined once again as coterminal. Okay, because they are on the same location. In other words, they both find themselves ending up at the same terminal side. Okay. So these are pretty straightforward. All right. Oh boy, there's more definitions coming. How about a reference angle? Now, you might remember some terminology from your travels. An angle that is acute means it's less than 90 degrees. The reason why they chose that name is because acute means sharp. It's a sharp angle. It's like if you had to drive up the hill, well, all right, anyway. There are a few others as well, though. Like, remember obtuse? Yeah, there's all kinds of names for this stuff. Acute is less than 90. A right angle is exactly 90, of course. Nobody ever forgets that. Obtuse is more than 90, up to 180. So the right angle is the one that's 90. The obtuse one, and God only knows why they picked that name. Obtuse is another name for not being very bright, but all right. It's greater than 90. But up to and including 180. And then after that, we have, oh no, that's it. Oh, I knew there were more. Okay. Oh man, what a flood of memories this is bringing back. Okay, so we also had the concept of the complementary angle. Two angles that add up to 90 degrees. And then we have supplementary angles, which add up to 180. Wow. Oh, it's been a while, hasn't it? But you learned this at one point in your life. And I thought I'd throw them in there. But remember, in this class, we're not overly concerned about definitions. But, when you see these words, you really want to remember what they mean. And there's all kinds of other stuff, too. We're not going to get to these. But, oh, I missed this one. Straight is exactly one. Oh, crap. See, now they wrote it very badly. They tricked me. This one should have been. Oh my God. All right. Now I'm annoyed with them. Let's write it like this. And then according to this, the straight angle, oh my God, is precisely 180. And then there's one more. According to this, the reflex angle is more than 180, but less than 360. Okay. Interesting. I don't remember those last two ever coming up when I was in school. I remember acute, right, and obtuse. I don't remember straight and reflex. But all right, if that's what they say. All right, anyway, and then complementary and supplementary. So now remember, again, the word reference angle is the smallest acute angle that can be created from that terminal side and that horizontal axis. So for example, if your angle here is 45, that's your reference angle. Here, if you're looking at 135, then the reference angle is 180 minus 135, which is 45. Here, if you're looking at 225, well, then your reference angle is 225 minus 180. And then finally down here, if you're looking at 315, then you're looking at 360 minus 315. Your reference angle is also 45 degrees. And that means with respect to that axis. Okay. All right. So again, we don't want to spend too much time memorizing things, but you might run into these. And then, of course, this can be redefined in terms of radians as well, because now all of a sudden, instead of subtracting everything from 360, we're going to subtract it from these radians instead. So they didn't give us a separate graph, which is kind of unfortunate. Let's see if we can do it ourselves. Oh, no, I didn't want to go that far. So just all we have to do is replace this with pi radians and then 2 pi. And you end up with the same thing. Okay. So like if you had pi over 2, 3 pi over 2. Oh, that's not 3 pi over 2, sorry. That would be 3 pi over 4. So when you're subtracting, no, sorry, this is pi over 4. So that it would be pi minus 3/4 pi is 1/4 pi. And then here, you have 5/4 pi. The reference angle would be 5/4 minus pi, which is pi over 4. And then finally down here with 7/4 pi. Okay, all right, so that'll do it. So again, let's not overspend too much time with this. All right, and then all right, so it's 11:30 now. I know this is getting to be a bit overwhelming, all this trig stuff. So here's what we're going to do. Between now and next week, why don't you work on the chapter 4 problem sets? And there's only one, I think. And then we'll do that next week to make sure we really understand 4. And then we'll get back into this, better ways to go. And, it's going to take us a while to get used to it all over again, because it's almost like you used to know how to speak French and you've sort of forgotten it. We have to get it all back into our memories before we carry on. But at some point, we're going to show you some interesting techniques for calculating all these different angles and all these different trig functions using something called the unit circle. And in fact, we're going to watch at least one video, which will help us understand how that works. And so the goal of this section is not just to throw a bunch of definitions at you, but to help you understand exactly how this stuff works. So anyway, don't be scared when we get back. What's coming will be kind of straightforward. Up to a point, but I think we got the worst of it done, all the definitions and trying to remember how all this stuff works. So let's call it quits here. And I think also you learned some important history today. And also, you know more about clocks than you ever did before. So anyway, I guess if there's no last minute questions, I'll see you all next Wednesday. Okay. You're welcome.
Thank you, Professor, for class.
Okay, see you later.
See you later. Feel better, sir.
Mm-hmm.
Feel better.
Been in a rough shape for the last couple of days. I'll try my best to get better.
All right. Take care.
See you later.